Hello and welcome back to the course on Classical Electrodynamics, and this is lecture 2 of the series, and I shall start from where I left in the first lecture, the second part. I shall begin with the equation from where I left last time. We saw that f can be written as the negative gradient with respect to A of EA EB by R AB, and that is we saw that this can be written as the negative gradient of EA EB by RAB as the summation over all the charges when B is not equal to A. And then from this we stated that if we could take out EA outside, we could take out EA outside, and we would have summation over B not equal to A or EB by RAB, and we recognize this thing as the potential, and we substitute for this, we introduce this term as the potential at the point RA, and as we proved earlier that if as I switched from the field concept, as you remember from the last, you may remember from the last time that we talked about approaches to electrodynamics, which is the action which may be action at a distance perspective, or as introduced by as the action at a distance point of view, or is the field or the local point of view, field perspective, which is introduced by Faraday, and so this could be written now as minus gradient with respect to A of EA of phi of RA, and so we proved that the self-action term actually doesn't contribute here, and so we are consistent in our work. So that is something that we proved last time. And so now the electric field I will define the electric field now, which is a negative gradient of this potential phi of RA, and phi of RA, but I shall not write phi of RA, I shall write in a continuous form. I should write phi of R, and so the force at a particular point A is charge times the electric field. So electric field reduces to the force per unit charge mathematically. At least we can say that. At least mathematically we can say that. And so the electric field is basically can be now written as E B multiplied by RA minus RB divided by modulus of RA minus RB squared. So this is the electric field, and as you see, you can multiply this with this, you get the Coulomb's law. So in fact, this is we call this directly. You can see it is directly in the Coulomb's law, basically. As I wrote E as the gradient of a potential, one thing is clear from vector calculus. One thing is very clear, and that is that if I take the curl of the electric field, that's going to be the curl, but the minus can be outside, so the minus of the is the curl of the divergence of the gradient, and the curl of the gradient is always 0, as we know. And why is it 0? I know many of you may be knowing this, but as I said in the beginning of the course, that I shall be covering the minute mathematical details, and also it's a revision or just review for other people who already know why the divergence of the curl of gradient is 0. It is because you could visualize this in a way that gradients do not, curl means how much it circulates. Okay, so how much it circulates, and a gradient is always perpendicular to the contour lines, and so it's always in a straight line, not a curl, and hence the curl of this thing is always 0. That is one way you could visualize it. And the second way is by manually computing the divergence by component, because we know that the curl of any vector A can be written in a matrix form as for example, I'll do it in Cartesian coordinates. So it is this. It is A sub x, A sub y, A sub z. Well, these are the components in x direction, y direction, and z direction. So basically, this is the curl, and so if you curl with the if you calculate the curl of the divergence, of the gradient, and the gradient basically is a vector, so it has components, just to remind you of, in Cartesian coordinates. It has the components partial phi, partial x, x cap, and there's the component partial x, partial phi, partial y, y cap, and partial z, z cap. So you can calculate the curl to be 0. If similarly you want other coordinate systems, or you want to do it in curvilinear coordinates, general curvilinear coordinates, you can do it, and you will get it as 0. Okay, that's for this thing, and this has become one of our first field equations. We call them field equations. So this is basically field equations, and we call them field equations because as you've seen, I have dropped the things over here, and now this is I'm using the field concept already, and without the field concept, essentially you will not be able to talk locally about the properties, and you will not hence get the Maxwell's equations that we are searching for. We are primarily searching for in this course. So that was about it, and about the next thing. The next thing is that, well, I need to give you a certain idea. Again, many of you may already know from your undergraduate courses or from your undergrad courses on classical electrodynamics, but it is just again a reminder for them, or it may be new to you, or the approach may seem new to you, or you may not have understood it clearly. Let's say at the Griffiths level, of course, I would say that you would not have understood the concept of a solid angle very clearly, because the book doesn't explain it that good. If you have only did that, and if you've done a course on multivariate calculus or of these things, and then I suppose you would have an idea of it. Well, I shall begin with that. And so, what is solid angle? We have heard about angles, but angles are two-dimensional. And I want you to imagine this situation in your head. It's a circle, and you have an angle theta subtending some length L here, and suppose this is a radius. So we all know the relation among this. We know that theta is equals to L by R. L is the arc length, and the arc subtended by this particular angle in the sector of the circle. But this is two-dimensional. We all know this. What about, say, I draw a sphere, and I ask you that if I take say a cone here. If I take a cone here, subtending some area A, and this is a radius R, what is this whole circle-like measure, or this thing? This cone will be something like this, and hence the bottom will be like a circle kind of thing. I can have circles over here, and the contour lines are basically circles. So, do we have a thing analogous to this in this? Do we have something analogous to this? Well, the answer is yes. It's used majorly in astronomy. When you're talking about scattering cross sections, you always use in classical mechanics, in Rutherford scattering, maybe if you have studied classical mechanics at MSc level classical mechanics. If you have studied scattering angles and all those things, you have probably seen it, but I assume that you haven't. So this solid angle is noted by this capital omega, and this is written by A, this area A subtended by this radius R squared, and this thing over here is called solid angle. This is considered to be analog. It's a 3D analog, or I should say 3D analog to arc. We are seeing over here the 3D analog to an angle. Well, this is measured in solid angles. For solid angles, we write ST, and then we write steradians. So this is measured in steradians, and this is measured in radians. Well, that is the most used unit, and for this is the most used unit, and steradians. And measured it in steradians, and this is radians. And well, in spherical coordinates, since it's a circle, it's easy to do in spherical coordinates. An element of this solid angle can be written as sine theta, d theta, d phi, where these angles theta and phi, well, I would describe them as something like this. If this is the circle, and if this is the point, and if this is this, and so I should write this as I should write this one. Well, theta is the co-latitude. This is the I don't know the name for that, but is the this is called the angle from the x-axis, and this is from the z-axis. So this is the y-axis. So that's the thin notation that I'm using, and well, phi is basically, this can be written as in well, since it's two dimensions, we have a surface integral. So from, well, in Cartesian coordinates, you have r cap by n cap r squared equal to this is same as sine theta d phi. Well, so r cap dot n cap is basically this is normal component of r cap. R is any vector over here, so r cap dot n cap, magnitude squared. And so sorry for that. Yeah. So yeah, sorry for that. Sorry for the disturbance. Well, this is the element of the solid angle, and I shall be deriving some results. I am deriving something called the Gauss theorem. Gauss theorem, and Gauss is Gauss is divergence theorem. Divergence theorem. So well, so consider a cone over here, and you see, consider a cone over here, and you see the many electric fields that lines that pass through it, and if a charge is, say, outside of it over here, or if it's here, or if it's here, or if it's here, let's say anywhere, I will measure that, or if it's a collection of charges. So what I do is I take a surface with a contour integral, or contour integral over ds dot E of r, and this is the flux. This is basically the flux. As you could imagine, this as a liquid kind of passing through anything, and you want to measure how much of the liquid actually passes through, and this is equal to, well,